In this video, we're going to be looking at topic 4b, the alkanes, which is part of the IAS chemistry course from Edexcel. So we're going to be looking at the alkanes and cycloalkanes in terms of their general formula and saturation. We'll be looking at some isomers, how we can use these as fuels, and then what pollutants can be caused by the combustion of these fuels. The problems that are caused by these pollutants, and then why we want to develop alternative fuels, and then looking at the reactions of alkanes with oxygen, halogens, and looking at the mechanism of free radical substitution reactions between an alkane and a halogen. So let's start off by looking at crude oil. Now you'll have covered some of this back in IGCSE, so again some of this may be revision, but there will be a couple of things that are new to the A level. So we know that crude oil is a mixture of different hydrocarbons of varying chain lengths. So we can go from having just one carbon in the chain up to having about 100 or 80 carbons in a chain. The crude oil is a finite non-renewable source because it is a fossil fuel, and we know that it is going to eventually run out because we cannot replace it in a human lifespan, and it is formed from the remains of ancient marine life. You're not required to know how it is formed. That is a GCSE style question. We need to know mostly that it is a mixture and then what we can do for it. So the hydrocarbons that are within crude oil have specific properties, and we can see different properties depending on the length of the carbon chain. And what we see is that as we increase the hydrocarbon chain, we see an increase in the boiling point. We see it becoming less volatile, so it doesn't evaporate as easily. They become more viscous, so they do not flow as easily. They become darker, and the flammability decreases, so they're not going to catch fire as easily. And this is because we get an increase in intermolecular forces, and you'll cover this in topics 7a and 7b. So we don't need to go into too much detail about it just now, but you need to know that it's the intermolecular forces that cause these trends. So crude oil on its own is not particularly useful. It is a black, sticky substance, very viscous, and we don't actually use it for anything. What we have to do is we have to separate it down into fractions, and we use a process called fractional distillation for this. And the fractions are mixtures of carbon chain lengths that are very similar, therefore giving them similar boiling points. So the separation process based on boiling points is our fractional distillation. And this link is a good link to a video about fractional distillation, and I will put that into the description so that you can have a look at it. It's a nice clear video explaining the process. So we get something that looks like this for fractional distillation. So this is our fractionating column. And these columns in real life are huge, and they have a temperature gradient. You can see that we go from cool, about 25 degrees Celsius, down to very hot at about 350 degrees Celsius. And we get different fractions coming out depending on their boiling points. So this is the separation. So we get refinery gases, gasoline or petrol, naphtha, kerosene, diesel oil, fuel oil, and what we call residue or bitumen at the bottom. And we see these same trends that we've previously discussed. So we get low boiling point, very volatile, easily flows and easily ignites at the top. And as we increase the chain length, we're increasing those intermolecular forces. So we start to see high melting points and boiling points, not particularly volatile. They don't flow very easily, and they do not ignite easily. Now, when we have fractional distillation, we've said that the column has a temperature gradient, and what happens is the crude oil is heated until it boils or is vaporized, and then these vapors pass into the fractionating column. And then depending on their boiling point, the hydrocarbon will travel up the column, and it will eventually undergo condensation, and where it condenses, it will then be collected in a tray and then taken out of the fractionating column. So we're separating the crude oil based on the boiling points of each hydrocarbon, and really that is another way to separate it using the chain lengths. Now, it's not exact that if you have one carbon, it will come out at the top and two carbons would be below it. It tends to be mixtures of varying chain lengths from about a difference between 1 and 4. Now, when we get these fractions from crude oil, after we've underwent fractional distillation, most of them can be used as fuels, for example, gasoline or diesel. The problem is that some fractions produce more desirable fuels than others, so some of our fractions will make much more money than some of the other fractions, and we can't possibly predict how much we're going to be making. So what we want to do is we want to be able to transform the least desirable fractions into the most desirable fractions. And what we tend to find is the least desirable are the ones that have long chain lengths, because they have these properties that aren't particularly useful. They don't flow, they don't burn very easily, and they have a high melting point. So that's not really what we want. We want to be having most desirable chains, and they tend to be your short chain lengths. Things like your refinery gases or gasoline will have chain lengths up to about 8 to 10 carbons at most. So you can see here that when we look at the uses of crude oil, 43% is used as gasoline, whereas kerosene and asphalt, so this one being from the bitumen, and kerosene is its own, these can be 1 to 2%, but we can actually make quite a lot of this. So what we want to do is we want to break this up, and we do this using catalytic cracking. So cracking is a process in which long chain alkanes are converted into either alkenes or short chain alkanes, and sometimes we can also make hydrogen with this as well. How we do this is we heat the hydrocarbon in order to make it a vapour and make it into a gas, and we then pass it over a catalyst of silica or alumina. Sometimes we can also use zeolite, which is a mixture of the silica and the alumina, and we do this at about 600 or 700 degrees Celsius, so it's very, very hot when we do this. And the hydrocarbon, which tends to be paraffin, is going to be soaked into mineral wool, and what that does is it makes sure it doesn't react with the catalyst, and it also just helps keep the liquid in place. So we have the mineral wool soaked in the liquid and then passing over the catalyst. So we get something looking like this. So this would be a laboratory setup of cracking. So we've got our mineral wool being held in place here. It is then vaporized to form a gas, and then it passes over the catalyst. And our catalyst here is porcelain chips, which is a mixture of, we've got alumina and silica, and then these broken down gases are then going to pass through a delivery tube and to be collected over water. Now you could also collect it in a gas syringe, but we tend to do this by collecting it over water, and then we form our product inside the test tube here. So we can actually carry out this experiment in the lab, and the hydrocarbon and the catalyst are heated on and off. We need to remember that the hydrocarbon, because we don't use a particularly long chain, it is still quite flammable, so we don't want it to catch fire, we only want it to vaporize. So we mix between heating the catalyst and heating the hydrocarbon. One other key point that we have to be aware of, and this has actually come up in a Unit 3 paper, because you can be asked about this experiment in the practical paper, is that the delivery tube must be disconnected from the apparatus before the heating is stopped. So we need to take this delivery tube out here from this apparatus before we stop the heating. And the reason for that is we want to avoid this thing called suckback. Suckback will happen because the air pressure inside the delivery tube will drop once we take the heat away because it's cooling down, and what happens is it pulls the water back in through the delivery tube, and if that goes into the hot test tube, then the cold water touching the hot glass can cause the test tube to shatter. So this would be something that would be noted in a risk assessment, making sure that we don't want this suckback to happen and we have to remove the delivery tube and then turn off the Bunsen burner or remove our heat source. Now, when we're looking at a cracking experiment in terms of what we actually make, what we need to make sure we have is that the number of carbon atoms and the number of hydrogen atoms on each side of the equation are the same. So we're not actually removing any of the carbon or hydrogen. All we're doing is just breaking it down into shorter chains. We will also form at least one unsaturated alkene because we have not enough hydrogen in order to form two alkanes. So we will either make alkanes and alkenes, or we will make all alkenes and hydrogen. This one isn't as common, but you just need to be aware that it can happen. But the majority of the time, we will make a mixture of alkanes and alkenes. And we can see that here that we've got decane, C10H22, being broken down into C8H18 and C2H4. So we have an alkane and an alkene, giving us 10 carbons and 22 hydrogens, which is exactly what we started with. We can also process the fractions from fractional distillation by using a process called reforming. And this is the conversion of straight chain hydrocarbons into branched chain or cyclic hydrocarbons. And we do this by heating the hydrocarbon with a catalyst, usually something like platinum, in order to remove some hydrogens or to change the shape. And the reason that we do this is when we have branched chains and cyclic hydrocarbons, we get more efficient burning, or it helps in an engine with more smooth burning, but we tend to say that it's more efficient or it stops any knocking. Sometimes you may also hear. So an example here would be if we have pentane, which is C5H12, it can undergo reforming and I can make cyclopentane, which is C5H10, and I also form some hydrogen. Or I can have heptane, which is C7H16, and then I can make methylbenzene, and we have this benzene ring here, which is normally C6H6, and you'll learn about benzene in topic 18. And then we also remove some hydrogen here as well. So we're just reforming into a cyclic. And this one is not only cyclic, but it also has a branch as well. So it gives us more efficient burning. Now, when we burn hydrocarbons, we do that because they are being used as a fuel. And a fuel is a substance that, when burned, is going to release energy. And there are two different types of combustion, and you will have met these back in IGCSE. So the two different types are complete combustion and incomplete combustion. So the complete combustion of a hydrocarbon is going to form carbon dioxide and water. And remember, complete combustion means that we have a plentiful supply of oxygen, or in other words, the oxygen is in excess, and we have more than enough in order to make our carbon dioxide and our water. So we can see the two examples here. We have the complete combustion of methane to make 1 mole of carbon dioxide and 2 moles of water, or the complete combustion of octane, and we're making carbon dioxide and water. Now, the water is not an issue in terms of the product of combustion, but we do already know that carbon dioxide is a greenhouse gas, and you covered that back in IGCSE, and greenhouse gases are responsible for climate change, with carbon dioxide being one of the biggest factors contributing to climate change. So we do have some issues when we do burn these fuels. Now, incomplete combustion is when we're going to form carbon monoxide, or sometimes just carbon on its own as soot, and again we make water. And the incomplete combustion is because we have not enough oxygen. So we have a limited supply of oxygen. And the biggest problem with this is that we're going to form carbon monoxide. And carbon monoxide is a poisonous gas. It's poisonous because it bonds with the hemoglobin in our red blood cells, and instead of the hemoglobin acting as a carrier for oxygen, the carbon monoxide irreversibly bonds with it and stops it from carrying the oxygen. So it essentially poisons the hemoglobin, stopping it from doing its job. The small particles of carbon that we can get in the air as soot can also be very harmful. They can particularly be bad for respiratory issues. And sometimes not all of the fuel burns and it releases some of it unchanged, and we call these unburned hydrocarbons. And again, these are not particularly good for the atmosphere or for respiratory issues within the general population. In crude oil, some of the molecules can also contain some impurities of sulfur. And when we burn these impurities within the crude oil, we're going to form sulfur dioxide. And the sulfur dioxide can then react in the atmosphere to form sulfur trioxide. We can see that in these two equations here. So we have the sulfur reacting with oxygen to form SO2, and then the SO2 reacting with oxygen in the atmosphere to form SO3. Now, the problem with that is that these are acidic gases. So if we have these acidic gases in our atmosphere, they can dissolve in water and the moisture in our atmosphere, and they can form sulfurous and sulfuric acid, which contributes to acid rain. And acid rain can have some very damaging effects on the environment as well as buildings and structures, because it can produce corrosion. And we can see the two examples of the equations at the bottom here. So we're making H2SO3 and H2SO4. We can also have the substances having some nitrogen impurities. This isn't as common as the sulfur, but it can still happen. And when we have the nitrogen in contact with something like a spark plug in a car, so when we're using this fuel, giving us a very high temperature, we can make different oxides of nitrogen, and we would term these as NOx, where X can be varying numbers. But the main two are nitrogen monoxide, NO, and nitrogen dioxide, NO2. And we can see how these are formed from these equations. Now again, the nitrogen dioxide can dissolve in the atmospheric water, and we can form nitrous acid and nitric acid, and again, these will contribute to acid rain. Now these, as I said, are not as common as sulfur impurities, so the main contributor to acid rain are sulfur impurities, but the oxides of nitrogen can sometimes cause an issue. If you are asked in an exam about the gases that can contribute to acid rain, I would stick with the sulfurs. They tend to be the ones that mark schemes are looking for most commonly. Now, one way that we can overcome these issues is we can use something called a catalytic converter. And a catalytic converter is attached to the car exhaust system, and their sole purpose is to help reduce the pollution that comes out of the engine. Now, it cannot completely stop the pollution, of course, but if we can change some of these harmful gases that can be given off into harmless gases, then it works better for the atmosphere. So catalytic converters tend to be small quantities of platinum, palladium, or rhodium, which are transition metals, over a honeycomb mesh. And these are the parts that act as the catalyst. So they're completely unchanged in the reaction, and even though they are quite expensive, because we use them in such small amounts and we don't need to replenish them, then the cost helps balance itself out. And what happens is we have our harmful gases, our unburnt hydrocarbons, our carbon monoxide or our nitrogen oxides, passing through the catalyst, and we don't need to know too much about how it works at this point. We will talk about that later in topic 9. But they pass over the catalyst and they help convert them into nitrogen, carbon dioxide, and water. Now, although carbon dioxide is a greenhouse gas and it is not good for the atmosphere, it is significantly better than the carbon monoxide and the oxides of nitrogen. So we can live with the fact that we are giving out carbon dioxide as opposed to these completely toxic gases. Sulfur is not removed by these systems because they tend to be removed before the fuel is burned. So what you'll find is that the fuel, before it is actually put into an engine, or even before it goes into something like a petrol pump, can undergo a treatment to remove these sulfur impurities, or at least reduce them to very, very small amounts. Because we get so much pollution from the combustion of these fuels, we also have to consider the effects of the this on the atmosphere. We also need to look at when we're depleting natural resources and the overall effects in terms of climate change. So a lot of scientists are advocating the use of alternative fuels such as biofuels, because these are formed from renewable sources and we tend to have less pollution being given off. The closer a fuel can be to something known as carbon neutral, the better. And what carbon neutral means is it has zero net effect on the amount of carbon dioxide in the air, i.e. the carbon dioxide that it is taking in order to make the fuel is the same as that's being given out. So it's not necessarily that it doesn't give out any carbon dioxide, it is simply that it's balancing out the carbon dioxide it's giving out was what was removed from the atmosphere when the fuel was being formed. So examples of alternative fuels the most commonly tend to be bioalcohols, or we can also use hydrogen. Now, when we determine the best alternative fuel, we need to look at lots of different factors. And for biofuels, we're looking at things like land use, the yield, manufacture, transport, and of course, carbon neutrality. If we need to take up lots and lots of space and it requires huge amounts of energy or huge amounts of money in order to be able to make these fuels, then economically it may not be beneficial. So we need to balance out the economic benefits with the environmental benefits as well. We can also use hydrogen as a very useful fuel because when we burn it, we simply make water, and of course water is in our atmosphere already, so it is not a pollutant. But the biggest problem is that hydrogen gas, when we take it from water, requires energy in order to do that. So to get hydrogen gas from water, we need to do electrolysis. And in order for it to undergo electrolysis, we need energy, and we get that energy from fossil fuels. So in reality, whilst hydrogen is a good fuel, where we get it from causes more fossil fuels to be used, so therefore it's not as useful. And another problem is the storage of hydrogen. Hydrogen typically, as we know, will exist as a gas, and we can store it when it's pressurized, but as soon as we start to pressurize the gas, we potentially cause it to become explosive, and hydrogen can combust with oxygen quite rapidly and cause quite a large explosion, so we do need to take that into account as well. So we can compare something like bioethanol with natural gas when we're looking at a fuel for cars, and this could be a possible exam question worth maybe 3 or 4 marks. So when we're looking at bioethanol, we need to use lots and lots of land because these tend to come from things like sugarcane, and we have to grow the sugarcane. If we compare this to natural gas, we do not use any land at all because natural gas comes from underground sources. In terms of yield, the yield for bioethanol is quite low, but we tend to increase it, whereas the yield for natural gas is very high. The manufacture and transport for biofuels is the fact that we don't need any exploration or drilling costs, so we completely cut down on that, but there are substantial costs in terms of growing, processing and transporting the fuels once they are made. Comparing to natural gas, we have huge costs for exploration and drilling in order to find the natural gas. Processing costs are quite low, but transport costs, although they can be low, we have to build a pipeline in order for the gas to be transported, and sometimes that can be slightly higher in terms of the cost. And looking at carbon neutrality, biodiesels and bioethanol are much closer to being carbon neutral, not quite carbon neutral, but much closer, whereas natural gas is definitely not carbon neutral because, of course, it is a fossil fuel. So let's move on to look at the reaction of alkanes with halogens. Now, what we find is that with the exception of combustion, when it's reacting with oxygen, alkanes tend to be very unreactive. And this is because they only have single bonds, so they are already saturated. So they tend not to undergo further reactions. However, one thing that it can react with is a halogen in a substitution reaction. And we call this process halogenation. Now, you met this back in IGCSE, where you had something like methane reacting with chlorine, and you learned a little bit about the substitution reactions. We're going to go into a lot more detail about it, and we're going to look at the actual mechanism of how this works and to show how the bonding in the alkane changes as we undergo the substitution reaction. So we get something like methane reacting with chlorine to make chloromethane and hydrogen chloride. And this process undergoes a mechanism that requires 3 steps. Now, the 3 steps are known as initiation, propagation, and termination. And you need to be able to explain and give examples of all 3 steps. And this is known as free radical substitution. So it's a substitution reaction, and the mechanism is via free radicals. So for step 1, the initiation, the part to start it off, is using ultraviolet light in order to break up the chlorine molecule. So we know that chlorine is a diatomic and it exists as Cl2, and ultraviolet light is then used to break that up into 2 chlorine free radicals. And this is done via homolytic fission. And we learned about homolytic fission in topic 4a, where we have an equal sharing of the electrons. So we get 1 electron going from the molecule bond into each individual atom. And we get this free radical. And a free radical species simply means it has an unpaired electron. And we term it using this notation here. So we write the symbol and we write a dot next to it. And sometimes we can show this using something called a half curly arrow. Now you're going to learn about curly arrows in much more detail when we look at other mechanisms, but curly arrows simply show the movement of electrons. And when we have a half curly arrow, this shows the movement of a single electron. So that we have 1 electron moving from this bond here to each individual chlorine to make my 2 radicals. So that's the initiation step. Step 2 is propagation. Now what we need to understand is that a free radical is extremely reactive. We know that molecules do not want to have unpaired electrons, so free radicals want to react and remove this unpaired electron or bond it with something else. And what happens is the free radical collides with the CH4 methane molecules, and they will remove a hydrogen. And by removing a hydrogen, they form a methyl free radical. And they steal this hydrogen in order to bond with the chlorine free radical. So we have our chlorine free radical bumping in to the methane, stealing a hydrogen to form HCl and this methyl free radical. Now again, this free radical does not want to exist like that, and that will then react further with more chlorine, and it will steal one of the chlorine atoms from this chlorine molecule to make chloromethane, and we reform the chlorine free radical. So we are reforming here. Now, what we mean by propagation is that we have a cycle of steps. So you can see here that as soon as I reform this chlorine free radical, I'm going to go back up to the first step. That's going to happen again. And then I go back to the second step. I reform the chlorine radical. I go back to the first step, and so on and so on. So I go from step 1 to step 2 in my 2 reactions. So there's 1 and 2. And then I go back to step 1 and then back to step 2. So propagation is this constant cycle, and this will continue to happen until we get to the 3rd step. And the 3rd step is known as termination. And this is when we have 2 free radicals hitting together in order to form a molecule. So rather than a free radical attacking a normal molecule, we're getting 2 free radicals colliding to make a molecule. And because we have 2 different free radicals, we have the chlorine and we have the methyl, we can get 3 possible combinations. I can get 2 chlorines to reform chlorine molecule. I can get a chlorine and a methyl to make chloromethane, or I can have 2 methyls to form ethane. Any one of these could possibly happen. We can't possibly predict which one is going to happen. And this is known as a termination step because my sequence of reactions stops because my 2 reactive species, i.e. my free radicals, are converted into an unreactive species, i.e. the products. Now you can see that we get some unwanted products here, but that's okay. What we want to focus on is the fact that we go from free radicals to our products, and this is our termination step. Now this reaction has then given us our chloromethane. So we formed CH3Cl. So this is a substitution reaction because one of my hydrogens in CH4 has been replaced by 1 chlorine. So you met that reaction at GCSE where you had CH4 plus Cl2 to give you CH3Cl and HCl. Now you know how it happens. So it happens via initiation, propagation, and termination. Now with these particular reactions, what we need to understand is that it's very rare and that we actually just get what we call monosubstitution, which is where we get 1 hydrogen being replaced. We can get further substitutions happening, and we can form dichloromethane, trichloromethane, and tetrachloromethane. And we can see these here. And again, these all happen via free radical substitution. Now, in an exam, you will only be asked to ever write out initiation, propagation, and termination steps for monosubstitution. So this would be your exam mechanism. However, you could be asked what an issue is, and it's that we get further substitution. So we can get di, tri, and tetrachloromethane, but you wouldn't be asked to draw out the free radical substitution. So whilst this is a process for preparing a halogenoalkane, like chloromethane, it is not the best method in order to prepare these because we cannot make the exact one that we want. If we want to make chloromethane, we can't confirm that we're not also going to make di, tri, or tetrachloromethane. So in topic 10, we will look at ways of actually making halogenoalkanes, but this is just a process, it's just not the best process. Because we also get these extra products, so we also make the hydrogen chloride, chlorine, and ethane, then we are going to require separation techniques to be used, and we're also going to get a low yield and a low atom economy. So these are all things that we would take into account when we were making halogenoalkanes. So let's finish off by looking at some past paper questions. So the first is from January 2019, and this summarises the processes involved in the productions of alkanes from crude oil and then their uses. And we want to name the 4 processes. So going from crude oil to the naphtha fraction, well, that's going to be fractional distillation. Then taking that naphtha fraction and going to octane, so that's the breaking down into smaller chains, that's going to be cracking. Reforming the octane into cyclooctane gives us step C of reforming, and we can also make ethene into polyethene. Now we haven't covered that yet, we're going to talk about that in 5B, but you did learn it in GCSE, and we know that to be polymerization. So there is the 4 marks. So part B is looking for what happens to the compounds that are present in the crude oil during this process, and then what is the property that allows it to work. So the first part is the process in order to actually separate them. So we get evaporation followed by a condensation reaction. So we evaporate the crude oil, it passes into the column, and then we condense it. And the property that allows this to happen is we have the separation depends on the different boiling points. So it depends on the fact that we have different boiling points within our process or within our mixture. And the naphtha fraction comprises alkanes with a minimum of 4 and a maximum of 10 carbon atoms. Write an equation for the formation of octane and ethene in process B. The state symbols are not required. So let's start off with the products first. We know that we're going to make octane, which is C8H18, and we're also going to make ethene, which is C2H4. Now, we said back when we were looking at cracking that our number of carbon atoms has to be the same on the left-hand side and the right, and so does the number of hydrogens. So if I have 10 carbons on the right-hand side, I need 10 carbons on the left, and if I have 22 hydrogens, I need to start with 22 hydrogens. So that is my reaction. And there's the mark scheme for those questions. We're also going to look at another question to do with alkanes, and this is looking at the free radical substitution. So we've said that the reaction of methane and chlorine is an example of free radical substitution. What is the essential condition for this reaction? And the answer would be UV light or ultraviolet light or ultraviolet radiation, we can also say. And the first stage in the mechanism is shown here to make the formation of the free radical chlorine, and we can see that in the diagram, and we want to explain what a curly half arrow means. So we have a single electron. Remember, the half arrow or the fishhook arrow here tells us that it is the movement of one electron, so a single electron transferring from a bond to one of the chlorine atoms. So we're getting the electrons moving from the covalent bond into one of the individual atoms. That will give you 2 marks. Then we want to write the 2 equations for the propagation step. So this is where you will find in past papers they always ask about the chlorination of methane. So if you memorise the propagation steps and the termination, you're very likely to get a decent mark in one of these questions. Now, of course, they could ask you about something different, so always make sure to read the question carefully, but they will all form the same basis here. So we know that we're going to have the chlorine free radical reacting with the methane, and it's going to take one of those hydrogens, so we're going to form hydrogen chloride, and then that leaves us with our methyl free radical. This methyl free radical will then react with the chlorine, stealing one of the chlorines to make CH3Cl and reform our chlorine free radical. And we know that then that will cycle back round, and that's our 2 propagation steps. And chloromethane is also found in the termination step of the reaction, and explain why the amount of chloromethane formed in the propagation is much greater than the amount formed in the termination step. So we have 3 different points here. So for the first point, we want to say that in the propagation step, we're going to get 1 chlorine free radical produces 1 molecule of the chloromethane and a new radical. So this happens in the propagation step. So we're making the chloromethane plus we're making a radical. So the fact that we're making this new radical, this means that the propagation keep repeating. So we're getting this constant repeating of the propagation steps, and that's going to then continue to form this chloromethane. Whereas in a termination step, we have two radicals making the CH3Cl, but this stops the reaction. So we don't get any more recycling here, and we don't form anything else. So we only make the chloromethane, whereas with the propagation, we get this constant repeating. So we're going to be making more chloromethane. And that's your 3 marks. And we can see that we have the mark scheme there, and there's a couple of different points about allowing specific phrases or ignoring specific phrases in the last part of the question there. So that's everything for topic 4b, the alkanes. Again, I would strongly suggest that you have a look over the initiation, propagation and termination steps for the chlorination of methane, and you practice writing these out. There are lots of past paper questions and questions in the textbook, and if you do have any issues with any of the content in this video, please feel free to leave a comment below and I'll get back to you when I can, and we hope to see you back on the channel soon.